Hello. I'm starting today's session by acknowledging the traditional custodians of the land upon which this festival is being presented. I also pay respect to Australia's First Nations, who we recognise as first scientists and custodians of the lands and environments and all animate and inanimate things within it. We acknowledge the importance their legacy, passed from one generation to the next for over 50,000 years, has on caring for Mother Earth and contemporary scientific conversations. I acknowledge the deep and timeless relationship between country and Aboriginal peoples and Torres Strait Islanders, and I also pay respect to the elders of the community, both Indigenous and non-Indigenous old people like me who are with us today. Everyone, I'm so rapt to welcome you to the World Science Festival Brisbane 2021, Physics, the Language of the Universe. It's so exciting. My name's Bernie Hobbs. For many years I've been writing and talking and demonstrating about science, but this afternoon we are in for such a treat because you guys are... What schools are you from? Tick, 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 that's the roll call done. Yep, got all that. So you are going to be hearing from not one, not two, but three brilliant physicists all from here in Brisbane. Let's hear it for brilliant physicists. Because I feel like we've got a few brilliant physicists sitting here in the audience just right now. Now, this afternoon, it's not going to be like a normal classroom. It's not going to be like a lecture or anything. You are going to be taken right the way out to the edge of our universe. You're going to see other galaxies, and then we're going to get down into the tiny quantum stuff. Have you heard of atoms? Of course you've heard of atoms. What do I think you am, grade 1? No, you've heard of atoms, you've heard of molecules, you've heard of electrons. Have you seen liquid nitrogen? Have you been 10-pin bowling? All right, you got it all covered. All of that is going on this afternoon, not from me, from our three special guests. Now, our first special guest is Professor Tamra Davis. Get on out here, Tamra. Now, you might get a hint from Tamra's outfit, but what kind of physicist do you think she is? Yell it out. She might be an astronomer, astrophysicist kind of gal. So Tamra is a professor, which is a very high up researcher at Queensland Uni, just over the river here. And Tamra has been working on, you might have heard of these little things like supermassive black holes. Yeah. A bit cool? A little bit cooler than that? Yeah, I thought so. So, and not only that, Tamra and a team of scientists all around the world have totally mapped not just Earth, not just Google Maps, not just the moon, not just the solar system, the entire freaking universe, okay? So, I know, and it's like even more galaxies than you see stars on her dress. So give it up for Professor Tamra Davis. All right, you might have also seen Tam on TV. She was on Catalyst. She was trying to go to Mars recently. You can catch that on iView if you missed it. It's a great show. I loved it. Our second special guest physicist here today is Professor Ben Powell. Come on out, Ben. Now, you know, I was saying Tamra is all about galaxies and stars and the big picture stuff. Well, Ben, you don't work with the big stuff. You work with the much smaller stuff, the little, atoms and molecules and all that kind of stuff, electrons, and you're going to do some incredible demos for us later. You might be making some noise, some racket.
Might make a little bit of noise.
Might be a loud explosion.
Are you guys ready to make some noise for me later?
So, Tam is all about the big universe, the big picture of the universe, but Ben is right down the other end of the scale, looking at how atoms and molecules, not on their own, but how they work together to make great stuff happen in our everyday lives, like blowing stuff up, okay? So we're pretty keen on that as well. So give it up for Professor Ben Powell. And our final professor is Professor Andrew White. Get on out here. Now, Andrew is a quantum physicist. Have you heard of quantum physics? Do you know what size it's about? Is it about the big stuff or the tiny stuff? Tiny, like tinier than... Were you giving hints there? Yeah, no, there'll be none of that. They know the answers already. So Andrew is working on quantum physics, he's working on lasers, he's working on shrimp, or prawns, as we call them, and a whole lot of other stuff. He's going to give a laser show. It's all going on there. So we've got Tam telling us about the big picture of the universe and the scale. We've got Andrew at the end telling us about the very, very tiny stuff and how that tiny stuff, that light, carries information that tells us about our universe. And we've got Ben dealing with the stuff in the middle, which is what happens when tiny stuff act together so that they can make things really happen. That's enough from me. Before we get cracking, I want to just acknowledge that Queensland Museum is proud to host World Science Festival Brisbane. Let's hear it for World Science Festival Brisbane. And we really want to thank our partners for their support. So let's give it up for the partners. Woo. All right, that is enough from me. Let's give it up for Professor Tamara Davis. Woo.
Hello, everybody. Good morning. Good afternoon, actually. Welcome. As Bernie said, I'm an astrophysicist, so I study space, which you can't see right now because there's a roof above us. And also because it's daylight outside. So I'm going to show you some pictures instead. This first one that we've got here, what's that? Earth. Now, that's obvious to us right now, but this picture was taken by some of the first astronauts that went to the moon. And can you see how you can't see all of the Earth? Some of it's in darkness. That's because the sun's only shining on the daylight side of the Earth, and the other side's dark. And usually we don't get to see that, right? Because we're on the Earth, we don't get to see it. And way back in the 1960s, people had never really seen this before. This was one of the first pictures that we saw of our planet floating in empty space and seeing it from this far away. So it gives you a real idea of us sort of in the emptiness of the blackness of space. Now, if we move on to the next one, we have another picture of Earth. But no, it's not Earth. It is. It's definitely Earth in there, but you might be confused because Saturn is in the way. Can you see Earth in the little corner up there? If there's a little dot, that an arrow might appear. That. So that's where you are at the moment. You're sitting on that little dot. This was taken by the Cassini spacecraft, so if you were out there orbiting Saturn in a spaceship or something, that's what Earth would look like for you. We have yet another, even further away picture of the Earth for you, though. Oh, sorry, before we go on that, we're going to have a quick zoom in on the rings of Saturn. And if you zoom in, see how beautiful the pictures, this was also from Cassini, how beautiful the pictures can be. See that? Does anyone know how big 4,800 kilometres is? It's about as big as Australia. So if you took Australia, you could fit it in like that little black section of the rings. It's the whole Earth is smaller than the size of the width of the rings of Saturn, let alone the planet. Now, and if we have another zoom in, there's some awesome photos that have been taken by the spacecraft that have gone out and looked at things. Here you've got see how at the top there you can see some things sticking up and some shadows?
Yeah.
Those are some things on the edge of some of Saturn's rings, and they're up to 2.5 kilometres tall. And these are things that are floating around there around Saturn. But if we go out further, there's that further picture of the Earth. This is the most distant picture of Earth ever taken. Can you see us again? There you are here. Where? That tiny little dot. That's the whole Earth, taken from Voyager, which is the most distant picture of the Earth ever taken. Voyager's left the solar system now and is on its way into interstellar space. Now, we have this big solar system with the Earth just being a tiny little dot, but that's only one tiny part of a much bigger galaxy. Our sun is one of hundreds of billions of stars in a galaxy very much like this one. Now, we haven't been able to leave our Milky Way galaxy to take a picture. So this is a picture of Andromeda, but our galaxy would look sort of like this if we stepped out beyond it. But we don't see it like this. What we see is a view from inside that spiral galaxy. And what we see here is that stripe across the sky is the Milky Way. And it's the Milky Way because we're looking edge on through a galaxy that we are inside of. It's pretty cool, huh? Now, do you see two like fluffs on the left there? Those are not clouds, but they're called clouds. They're called the Magellanic Clouds, and they are actually entire galaxies themselves, which are on their way to our Milky Way, and they're going to collide with our Milky Way. At the moment, they're sort of like orbiting it in the way of it coming in and mixing up their stars with the stars that are in our galaxy. That's pretty cool as well. If you go, but our sun is only one of hundreds of billions of stars in our galaxy, but our galaxy is only one of hundreds of billions of galaxies in the observable universe. This is a picture that's full of galaxies. It's what you get if you take a picture of a patch of empty space, but you point the Hubble Space Telescope and look at that patch for 11 days. If you look for that long, things that were just too faint to see before become visible, and you see a picture beautiful like this, where pretty much every dot you see is a galaxy. And so each dot you see, even the tiny ones, hold hundreds of billions of stars. Now, the light from those most distant stars has taken over 13 billion years to reach us. Does anyone know how old the Earth is? It's about 4.5 billion years old. And that means the light that you're seeing has taken more than that time to reach us. So the light that you're seeing has traveled for longer than the Earth has been around, before our star even turned on. So anyway, all of this beautiful structure that you see here is governed by gravity and quantum physics, as we're going to hear. But the part that I'm going to tell you about right now is about gravity. And we now can chuck things into computer simulations and simulate the formation of galaxies and clusters of galaxies and that kind of thing. So this is a computer simulation showing how gravity pulls things together. And here, each little puff on the outskirts is an entire galaxy like our Milky Way, forming a big cluster of galaxies. Wow. And we can now test our theories of gravity by doing simulations like this and comparing them to the pictures we took of space and seeing whether they match and figuring out whether our laws of gravity and stuff are correct. Now, the light that we're seeing comes to us in different colours, right? And different colours correspond to different wavelengths of light. Now, Bernie, would you be able to come and help me demonstrate some wavelengths? Okay, so this is a Slinky.
Has anyone seen a Slinky before?
Yeah.
It's very physics.
Yes.
Yeah.
So if I make a wave in this Slinky, it might look like this. Woo, that's a big one, right? And at the moment, we've just got one big long thing here. So red light has long wavelengths. This is a long wavelength. If I try to do it a bit faster...
Am I doing it too, or am I standing still?
You can stand still, I think, for this one.
Oh, yeah, I was
there we go. So is there 4 loops in that now?
Yeah.
Well, maybe 3. If I go a bit slower, there should be 3.
Are there 3 or 4? 4.
Ooh, now it's mixed up.
Oh, you're mixing it up, miss. Professor Miss.
4. Can I go faster? Can I make it 5? No, I can't go that fast. But that has a shorter wavelength because we fit more loops into there. And so the shorter the wavelength, the bluer the light. So the color of light is determined by the wavelengths that you have in the light wave. Okay, shall I let this go now?
Oh, do you want to what?
I was just going to let it go.
We're going to let it go, no.
Oh, do it. Should we try to see? We've got a bigger one, but I'm not... We tried this a bit earlier, and it wasn't great, but I reckon we should...
Should we try it with the really big screen? It goes all the way across the floor. World's biggest Slinky.
Ooh. Okay, let's go. Shall we go for a big wavelength? This is like...
I think I'm just going to stand still.
Okay. Pull it tighter.
Should I move too?
Yeah, go back. Hold your hand up.
Oh, hold my hand up.
And then move back.
And move backwards.
Oh, there we go.
Back.
There we go.
Oh, yeah.
Oh, yeah.
Oh,
Wow,
yeah.
there we go. We got a big one going.
Oh, and can you hear it when it hits the floor? It sounds like a space laser.
Okay, that's actually quite exhausting trying to get that to go. If you have wavelengths that are that long, you actually have. We're twisting it. Radio wavelengths.
We're not meant to do that. We're making a physicist cry
yours, all
over there. Got to treat the Slinky with respect, man.
There you go. But the longer the wavelength, the redder the color. And you can go outside of colors that we can see with our eyes. So if you go to long wavelengths, you go to radio wavelengths, the kind of stuff that if you're listening to the radio in your car or something like that, that is radio waves communicating. We can't see them, but they can carry information. And that's some of the things that we can see. Oh, now, in terms of energy, though, and gravity, I have one more demonstration to show you. Because have you heard, you guys know about energy, right? Do you know that energy can't be created or destroyed, it just gets transferred into different forms? I'm going to show you how gravitational energy, gravitational potential energy, can turn into kinetic energy. So I need some help for this. So if someone grabs, there's a string up there that's going to slowly come falling down. People have gone bowling, I heard. Has anyone seen a bowling ball here? Yeah?
Not one with a big hook in the top of it. That looks like trouble.
Okay, so if we attach this on here, what?
Are we going to swing
this
it out
gonna
over the
look good?
audience, Tam?
Yeah, should I swing it at you guys? I need to push you back. Okay. I'm going to do it sideways instead.
You probably get a better view. Yeah.
So what we're going to see is we're going to see gravitational potential energy turn into kinetic energy. So the gravitational one is just a potential energy. It's sitting still, and it has the potential to move, right? And I'm going to drop it, and it's going to swing, and kinetic energy is movement energy. It's speed. So it's going to go really fast when it's at the bottom of the curve, and then it'll slow down and stop at the other end, and it will come really fast back, and it will come back, and it should come back to basically the same place it left, because it will all be converted back into the gravitational potential energy. And so what I'm going to do is I'm going to start with it here.
Kiss that bowling ball.
Who thinks it's going to smash back into Tamara's face?
Oh, let's hope it doesn't.
So we'll see. I trust physics, and therefore I'm not going to flinch. Ready?
Take a photo. Okay.
Oh. Watch out, Tam! Watch out for your teeth!
Oh.
Okay. Should we try again?
Yeah.
Do we get okay, one more. Harder?
Higher.
You want to push it?
But that's good if it's above your head, it can't hit you.
Oh, if it's above my head.
Yeah, true.
How about there?
Ready? Oh. Oh, watch out, Tam! But, so, you were saying, Tam, that it goes faster at some parts and slower than others, but maybe, have we got anyone who likes to run down there?
Yeah, can I get it?
Okay, 2 kids, come up the side steps.
You two
All
up here. Up, there's
Up
there's
the
steps, or
side
you can jump up.
steps.
That's fine. Okay, so I've got a challenge for you. What are your names? Harper and Isaac. Okay.
Harper, you stand on this line. Isaac, you stand on this line. There we go.
And it's a very simple rule. It's
So
not a
actually,
race
step
to
1 meter
win.
forward. Start here. So you're going to have to chase this, and you're going to have to match its speed. So that means it will start off not super fast, and then it will get really fast in the middle, and then it will slow down and turn around and come back, and you have to do the same. Okay? Ready? Set, go.
Run faster, faster, faster! Slower, slower, slower! Turn around, faster, faster, faster! Oh, it was pretty
You both
close.
back. You didn't slow down enough. One more time. Ready? Set, go.
Run! Keep up with the ball! Keep up! Slow down, slow down! Turn around, come back!
Excellent running. Thank you,
How
Papa
was
Isaac.
that?
Good work.
How was
Okay.
that? So did you guys, Harper and Isaac, did you feel like you went faster in the middle and slower at the end? Did you feel that? Or were you just like... It's got a stitch.
Yeah.
Yeah,
So that's
totally.
using the gravitational potential energy to make movement happen. And that happens anytime you roll down a hill, when you swing a pendulum, when you drop a pen or anything like that.
When you're a galaxy sucking another galaxy into you.
And the same thing works to hold our Earth in orbit around the Sun and our Sun in orbit around the center of our galaxy. So that's my demo for now. Thank you, Ben. I'm going to hand over to Ben, who's going to show you some new cool stuff about the...
While Ben puts that away.
little
So
stuff.
remember I said before that Ben... Oh yeah, let's give it up for Professor Tamara. Hello. Gravity, galaxies. And remember before I said how Ben looks at how tiny things act together to make effects happen. Well, he's not talking about 2 or 3 tiny things. He's not talking about 100 tiny things or 1,000,000 tiny things. What's the biggest number you can think of? Bigger than 1 billion?
Put it on the towel.
But the towel gets used.
Bigger than a gazillion? A septillion. Don't even ask me how many zeros that is, but Ben is here to talk about the biggest numbers, way bigger than 1 billion.
Okay, we need to
Okay,
push the tablespoon.
so I'd like to start by asking you guys a question. Do you think if something was hitting you in the face right now, you would notice? Okay, I'm going to show you that you're all wrong about that. Okay? Something is hitting you in the face right now, and none of you are aware of it. Okay, so what we're going to do is do a little demonstration of this. So thank you, Tamara. So this is just an ordinary camping stove. I can turn it on like that. And this is just a tin can. You get to keep your oil in your car in. And this is some water. And I'm just going to put a little bit of the water in here. Okay. Just put it on there, and I'm going to let the water boil. Okay. And so you are made of tiny little things called molecules. The air is made of tiny little things called molecules. Everything in this room is made of molecules or atoms. And what I'm doing in here is I'm heating the water in the bottom, and that's heating up the molecules in the water. And those molecules are starting, as they get hotter, when things are hotter, they move around quicker. When they're colder, they move around slower. And so the molecules inside the water are starting to move around quicker. And there's also lots of molecules in the air, and they're flying around, and they're banging into things all the time. Right? So there's little molecules banging in the air, flying around here. They're so small you can't see them. You need some of the most powerful microscopes in the world to see them. And they come along, and they're banging on the sides of the container, and it's a little bit warm, and then they go away again. And what you can see, you can just start to see maybe, if you're looking on the screen, I don't know how well that comes out on the screen, there's a little bit of steam coming out the top. Can you see that? And that's what's happened is some of the molecules in the water have got so hot that they've started to fly around really fast, and they're coming out of the can as we heat it up. I'll just let that carry on for a little bit longer. And so as the molecules are getting hotter, they're flying around faster, and they're banging harder on the inside of the can. And lots of them are coming out, and that's to keep the banging on the inside of the can and the banging on the outside of the can. It turns out nature wants to keep them to be about the same. Okay, so we've got a lot of steam coming out. I'll turn off the thing and put the lid on. Okay, and I'm going to screw this on and try my best not to burn myself. And I get my friends over here to come over and help me, because it's quite a subtle thing I'm going to show you, and that you might not quite be able to see it because you're a long way away, so I want these guys to make sure they help you notice what happens. So I'll put this is just some cold water, and then I've got some more cold water here. And so what I'm going to do is I'm going to cool down the water molecules inside the can. And so if you remember, I said when I heated them up, they got faster, and they're banging hard on the inside. And now that I'm cooling them down, they're going to start going slower. And so they're going to start banging more and more gently. Okay?
It's pretty incredible so far.
Isn't this literally the best science demonstration you've ever seen? Someone pouring water on a can.
Yeah, it's like a waterfall.
What's going on?
expecting rain.
So look what I've done to the can. I've completely crushed
Whoops.
it. Right? And that... Okay.
And it's a steel can.
Right. And that...
Setting a 10%
That is
deposit
the
payment.
pressure, that's the banging of the molecules outside the can. When I cooled down the molecules inside the can, they weren't banging on the inside very hard anymore, and the molecules outside the can were banging really hard on the outside the can, and that was such hard banging that it was able to crush this can. And
Wow.
exactly the same banging is happening on your faces right now, and yet none of you
Yeah.
are noticing it. So you need to pay better attention if you want to become scientists.
Oh, well done.
And so what I want to show you today is that if little things all work together, they can do really amazing things that seem almost magical. And that applies to molecules in the air, and it also applies to people. If I stand here and start stamping my feet, it's not a very loud noise, even though I'm stamping as hard as I can. But there's only one of me, and there's lots of you. So if you guys will start stamping your feet on the floor, okay, then you make an awful racket. And so working together, you can do something that I can't do. Okay. So if I'm going to convince you that lots of things working together can do magic, I'm going to need what all good magicians need, which is a volunteer. Would anyone like to be a volunteer? Okay, you in the front row, yes?
Up the
If you
stairs
the
on
stairs
the
are
side?
just up there.
This way?
Do you want me to take the bowling ball out of the way?
Yeah, that would be great.
This way? No, in front. This way?
Okay, so because of COVID, I can't touch anything that you're going to touch, and so I'm going to stand away from you. Okay, what's your name though? Cola? Lola. Well, nice to meet you, Lola. That's a more sensible name than Cola, isn't it? Does everyone give Lola a big round of
Yay.
applause? Thank you for coming up here. So you're going to do my next magic trick for me. Is that okay? Have you ever done magic before? Oh well, we'll see what we can do. Not even a little bit of magic? Okay, so it's all easy, don't worry about it, okay? All I want you to do is to start off, take this towel off the table, and there's some things underneath it, try not to knock them over. So just take them off, you can throw it on the floor or whatever, it doesn't matter. Thank you. Okay, so the first thing I need, these two blocks are going to do our magic trick. So I want you you can pick them up, touch them, tell me how they feel. Do they feel different from each other? So you can have a good feel. That's it. Let's feel the other one. Feel the other one too. Do they feel different in some way? What's the most different thing about them? Okay. And how about, does one of them feel
Ben,
hotter?
can you
or...
just repeat what Lola said?
Oh, sorry. She said this one feels a little bit more bumpy.
Oh, more bumpy.
And how about...
Maybe hold them in
okay,
your hands.
so she just said this one feels cold. So can you hold up for everyone to see which the one that is cold? This one? Okay, thank you. Yep, great. That's great. So put it down. That one feels cold. You're doing really well, Lola. Thank you very much. Okay, so now if you look behind you, there's a fridge. I'll open it for you. There you go. And if you reach into the fridge, if you look in the fridge, actually don't reach in yet, there's some ice cubes in there, right? Now, I'm going to ask you in a minute to pick up some ice cubes and put them on here. Don't do it yet, please. This one is cold and this one is hot. Which ice cube do you think is going to melt quickest? The one on the cold plate or the one on the hot plate? The hot. Okay, that's a great guess. It's a very sensible guess.
Well,
What does everyone else think?
hands up if you think hot. Hands up if you think cold.
There's some contrarians.
It's basic physics.
Okay, so we're scientists, so we're going to go ahead and do the experiment and find out the real answer. So pick up 2 ice cubes, please. And put one inside of each.
Wow.
So you can see, everyone I think can see this on the screen, that the cold one is melting really, really quickly.
Wow.
So thank you very much, Lola. You've been a great help.
Yay. Go, Lola. You're a legend.
Okay, so as I'm not really a magician, I'm a scientist, I'm going to tell you how I do this trick. And the trick is, which Lola really almost gave away at the beginning when she noticed this one feels a little more bumpy, because this one's made out of wood, the one that's not melting and felt normal temperature, and the one that felt cold is made out of metal. Okay, and in both of them are made of molecules, like we talked about before with the barrel crush. But those molecules contain electrons. And the electrons in the wood can't move around very easily. It's like people queuing to get somewhere or trying to get into this theater maybe at the beginning when there's lots of them, and they're all stuck in place. When the electrons in the metal, however, they can run around like kids in a playground. And so when Lola put her finger on it, those electrons could carry the heat away from her finger, and that heat being carried away made it feel cold to her. But also, when she put the ice cube on the top, the electrons can carry the heat from inside the metal onto the ice, and that lets it melt very quickly.
So it's not that the metal is cold, it's just sucking heat out of our fingers when we touch it or out of the ice cube.
That's exactly right. It's pushing heat into the ice cube to melt it. So the fact that it feels cold is not really true. They're both at exactly the same temperature.
It just means it's more conductive. It's got more conductive.
Yes. Yeah. And that's why when you when your parents boil things on the stove, they use a metal pan to boil the water in, but a wooden spoon to stir it. Because you want the heat to go through the metal. You don't want it to go up the handle of the spoon to your hand because you'll get burnt. Okay. So that was somewhat cool, but I'm going to show you something much cooler. In fact, this is probably the coolest thing you've ever seen in your entire life. Because this is at about minus 200 degrees Celsius.
That's pretty cool.
Right, so I don't have anything to drop in there now because it didn't work last time. But so we have some more bits of metal in there, and they're boiling away. And before I do that, I need some more. I'm going to close this up for a second, and I'm going to get some more of you to volunteer. In fact, I'm going to get all of you to volunteer. So stay sitting. No, sit down. And we're going to start. I'm going to volunteer the people. I think there's a few teachers, so this is good, or parents. People sat in the end row up here. You can all stay seated for the moment. What I want you to do is put your hands on your knees. Just the people in the end up here. This very far right row for you. And when I clap my hands, I want you to stand up, put your hands as high up as you can, and then sit down again. Okay? When I clap my hands, so off we go. Just the people on the end. Very good.
Okay. Ben,
watch out for the seats.
Yeah.
You should warn people, when you stand up, the seat can fold up behind you. We had someone do this morning, and they missed the seat and found the ground.
So be careful.
So that was really good. Okay. Now I'm going to get the rest of you to help. What I want you to do is everyone put their hands on the knees, everyone in the whole room. Watch the person on your right, so this side of you. Watch the person on your right. When they stand up and do the wave, I want you to copy them, but only the person immediately to your right. If there's an empty seat, just ignore that and keep the next person. So, okay, off we go.
Nice. Oh. You guys were so much better than the high school kids. They just could not dance.
The high schoolers we had this morning, we did like 3 goes of it, and they never got it that good. So you guys are much better than that.
Yeah.
Okay, did you notice there was a big wave going across as you came across? Let's do it again, and all look at the wave. Sorry, people who got their drinks out. Okay, off we go. Watch the wave this time, everyone.
Oh, even better.
Ben,
Woo!
since it's working so well, do you want to start each end and have the waves go through?
Do you want to? Okay. Yeah. Okay. So Andrew's idea, because you're doing this so well, we're going to do something new. Are you going to start this wave?
Okay, so what we're going to do is when Ben claps, we want the people on that far end to stand up, and at the same time, I want the people on this far end to stand up. And then the new rule is if someone is standing up next to you, then you stand up, either side.
Yep.
Okay, get ready.
There we go. That's
They died. Okay. Well, that was worth.
interference.
Let's just push on.
Destructive.
Okay. And what's really amazing? The bits of metal we just saw in here before are things called superconductors, and they're kind of special metals. And when we cool them down, the electrons inside of them go in and start making waves, just like you did. So the electrons wiggle around in just a way to make a wave. And that wave obeys the rules of quantum mechanics, and it can do some really amazing things. And one of them is it can put electricity through without losing any of the energy of the electricity. That's why we call them superconductors. But something else, electrons in metals don't like changing the magnetic field inside of the metal they're seeing. And so Normally, the electrons try and resist that happening. And this is just a fairly ordinary magnet, like you might have at home on your fridge. And this is a 5-kilogram weight, and it's pretty heavy. I'm going to put it down.
But you've been working out then, so it's okay.
Oh, thank you. Yeah. It's looking good. And Tamara told you how important gravity is. And what I'm going to show you is that gravity is really puny. Right? Gravity is just a weak, pathetic force. You shouldn't worry about it. So this is just a tiny little magnet. And I'm going to pull this weight, this 5-kilogram weight, with this tiny little magnet. Against me is the entire Earth pulling down. So the Earth is using all its weight and gravity to pull down into the floor. I'm just using this tiny little magnet. Magnetism beats gravity every time.
Unless you're a galaxy.
Yeah. Well, then there's no, very little. And this is quite hard to take off. Okay, so we've got this. So superconductors, so that's an ordinary bit of metal, right? So it gets stuck on the metal. You've probably played with this kind of thing before. Some magnetic toys. Superconductors are, as the name suggests, really super, and they can do some cooler things. So here's a superconductor.
It's very cold.
And if I push it on, it's levitating right there. Have you got a good view of that? And it's absolutely, completely levitating. There's no trickery here. I can put this round in any direction.
Yes, what? Yes.
Ben, can you turn it upside down?
It wasn't working very well before. We'll give it a go. Actually, I'm not going to do that over liquid nitrogen. That's a really dumb place to do it. Yes, there we go.
Oh.
It's stuck on. Those have been implemented.
Wow. Oh, yeah.
Okay, and that's because
He's a wizard. He's a physicist.
instead of the electrons working one at a time, they're working as a team. Just like when I stamped my feet, it wasn't very loud. When you guys worked as a team, you were able to make lots of loud noise. Okay, and now we can do some cooler things, because there's very little friction with the air and none on the ground. I can do this, and I can do it like... yes, I can do it. So it's just like a fidget spinner, but it doesn't stop, really, right? There we go. It'll stop very slowly because of the friction in the air. But it'll go on basically for ages, like longer than I have patience. Okay, and what we have over here is some more magnets. They're in a big circle here, and these can do some really fun things too. So I bring this over, and I have to push down. It's actually quite hard pushing down like that. Wow. Now they're levitating there, but they don't want to change the magnet. So if I push it, they follow the magnet round and round, and we can do that.
Yeah.
Now, it may even be possible. There we go. Go over things in the middle. Pull that up a little ways. That's too hot. It's not working. Let's see if I can do this. Often fails, but let's have a go. Yeah, we almost. I've never seen that happen before. There we go. So you'll notice as they get the quantum wave only really lasts if they're cold. So you notice when they start to warm up, they start to not work so well.
Wow.
And so the take-home point, the thing I want you to remember, is you guys might be little, atoms are much littler, but when atoms work together, they can do absolutely amazing things, and when you guys work together, you can do amazing things too.
Yeah.
Beyblade.
All good?
Well
All right. How great was that? That's the story of when tiny things working together can have big effects. Very cool stuff. And now, so we've gone from gigantic universe scale to tiny things working together in a medium scale, a little bit of argy-bargy between magnetism and gravity. And now we're going right down to the quantum level with Professor Andrew White. So let's hear it for quantum physics.
Afternoon, and thank you, Bernie. So Ben was saying that when atoms work together, they can do things that you can't normally do. And one of them was superconducting, which is just super cool. We can also do that with light. Light travels in a straight line, so the first scientists to find out about light thought it was made of particles, which we now call photons. And the light from these lights up here, what do you notice about it? It's kind of going all over the place. It's blurry. It's kind of big light spots on the walls and on the floor, which you can't see, and at the back if you look. But if you make all of the photons work together, then you can get the light to go in a straight line. And can people see the green dot over there? That, of course, is a laser. So we're used to that. I'm not going to put it any closer to your eyes because, you know, blindness. So don't ever look into a laser with your remaining eye. Okay, here we go. Yep, there we go, nice and green. But, of course, light can also behave like a wave. So in the same way that if you see a water wave go through some rocks, it breaks up into a lot of little waves, you can get a laser beam to break into a whole bunch of little spots. And that what we're doing there is we're moving tiny little slits in front of the laser light and making it break up into little bits. So light can behave like a wave or like a particle, depending on what you do with it. Now, thank you for that. Can we have a red light on the ceiling, please? So Tamara talked before about the fact that when you looked at the galaxies, and can we kill the stage lights, please? So I'd like you all to look up at the ceiling. And we talked about before how light can carry information, and some of the information it's carrying now is that the light is red. And that tells us that the ceiling's red, and we're seeing that with our eyes. Can we please go through to full green now? Okay, so that's quite nice. So how many people here at home have an iPad or a phone or a tablet? Or how many people have accidentally spelt water on it? Oh, your poor parents. Okay. How many people have dropped it in a toilet? Oh, really? Oh, no. Okay, so if you spill a little bit of water on your tablet, you'll see little red or green or blue dots. And what that is doing is each of those dots carries some information. And now can we have half red, half green, please? And so when you mix red and green light together, you get yellow. Okay, so if I need to make yellow light on my computer display, I mix red and green. Can I go back to full green, please? So that's full green, very nice. Now, if we go, please, to full blue, which is the other color, very nice. Turn to the people next to you and ask them, what do they think will happen if you have half green and half blue? Go, talk. Okay, someone yell out some answers. What colours do you?
Someone said aqua.
Oh, that's enough yelling. So what I heard was, is it the colour we're picking? All right, so I heard purple, I heard pink, I heard aqua. Aqua, let's find out. Can we have half blue, half green, please? Turquoise I heard, and we have cyan, which is kind of aqua. So it turns out the three primary colours when you're mixing light together to make any colour is red, green, thank you for bringing the lights up, is red, green and blue. But when you're mixing paints together, you use cyan, which is that light blue, yellow and magenta, which is a kind of pink colour. And if you look at your printer inks, if you've got a printer at home, they're cyan, yellow, magenta. So when you're mixing paint together, those three colours will make any colour. When you're mixing light together, you use red, green and blue. Now, if I was a dog, would I have seen all of that? No. And why wouldn't a dog have seen that?
Because you're not allowed inside the auditorium.
Because they see less colours than we do. And we feel sorry for them, the poor old dogs. We say that they see the world in black and white. It's not quite true, but they see less colours than we do. But it turns out we see a lot less colours than other animals on the planet. There's a thing on the barrier reef about this long called a mantis shrimp. It's got a big claw. They're also called finger snappers by scuba divers because they can break your finger. If you want to see a broken finger, Ben, can you hold up your pinky? That's what a broken finger looks like. Not from a mantis shrimp, he just caught a cricket ball wrong. These things have such strong claws that when they make bubbles underwater, the bubbles implode and cause an explosion of light. They're weird little things. But the other thing is, in each of their eyes, they've got eyes on stalks, kind of like if you held a tennis ball at the end of each arm and moved it around, a bit like a snail. Yep, perfectly. Their eyes can see not red, green, and blue, 3 primary colours, they can see up to 12. All the way from ultraviolet light, the stuff that burns your skin, through to infrared light, the stuff that feels like heat, and all of the colours in between. So they see a lot more of the world than we do. And so we are dogs to mantis shrimp, so to speak. I've worked with mantis shrimp in the labs, and they're really good because they're one of the very few experiments which, when you're done with them, you can eat them. Okay, but the other thing they do is they can see extra information. Can I borrow Bernie?
Yes.
And the short spring. There we go. So before, thank you, Bernie.
Am I just holding it still?
You're just holding it still. So before we were seeing that information is coming in light and the colour. And Tamara said that if we had a very long wavelength, that was like red light. And if we had a very short wavelength, that was like blue light. But there's other ways we can see that there's information and light. And one of them is the direction that the light field, the electric field of the light, is going up and down. So if I wanted to send a 0, I could say, if you see the spring going up and down, we'll call that a 0. And that if you see the spring going side to side, we'll call that a 1. And that's how you could send digital information, 0s and 1s, through the light. Okay? That's called the polarization of the light. Who here's got polarizing sunglasses? Oh, wow. Who's here's parents have polarizing sunglasses? Okay, so if you've got polarizing... We'll come back and do a bit more in a minute, Bernie. Yep. Don't go anywhere. Stand there.
Do you want me to hold that?
Thank you. So if you have polarizing sunglasses and you go outside and you look at this blue sky with no clouds in it, and if the sun is up here, look at 90 degrees from the sun. So if the sun's straight overhead, look around on the horizon. If the sun's down on the horizon, look immediately above you. And if you look with the polarizing sunglasses and you turn your head side to side, you'll see a black ring around the sky. And that's due to polarization. And bees can see that ring. So what bees do is they look at it and they use that to tell directions. So they'll be on a flower, they'll look up, they'll see where the sky is looking blacker with their polarized sunglasses built into their eyeballs. Then they'll fly back to the hive. And do you want to demonstrate, or shall I?
Yeah, they get out their tiny little mobile phones and go...
No, they don't do the tiny little... Okay, I'll do the dance. So they do a little bum dance that shows from how far they wiggle their bum and which way they wiggle their bum. The other bees, they basically tell the other bees, go out, look at the sky, and from there you can figure out how far and what direction to go to the flower.
Wow.
So polarized information is really useful. Now, how do the polarizers in their eyes work? Now, I need 2 volunteers. I need 1 student and 1 teacher. Okay, young lady here in the red. Young man, I can't tell. Okay, yes. And 1 teacher.
Over to the stairs, teacher.
Over here, teacher, please. Excellent. Thank you very much. And your name is? Cameron. And your name is? Mrs. Gordon. Okay, round of applause for Cameron and Mrs. Gordon. Okay.
Cheers.
So, Cameron, can you come stand in front of this spring and face towards the audience? There we go. And Mrs. Gordon, can you come and stand behind the spring and put your back next to Cameron's? There we go. So, Mrs. Gordon and Cameron are now going to act as a polarizer, and that is something that will tell us about the direction of the light. So I'm going to try and send a signal through to Bernie, standing on the other end.
I'm ready, I'm waiting.
And
Here
if I
it
send
comes.
through a vertical thing, it goes through beautifully. Mrs. Gordon, Cameron, can you move slightly closer together? Slightly closer together? Oh no.
Yep.
Okay,
That's
perfect. A little bit closer. Perfect. So, vertical signal makes it through, but now if I try and send through, sorry, Mrs. Gordon, a horizontal signal, you can see very little of it's making it through to Bernie, right?
Can you guys turn and see that? It's not coming through.
I can send through the 1, it goes through, but I can't send through the 0. Okay. What if I wanted to send through something that was a mixture of 0 and 1? 0 plus 1 is like a diagonal. Okay, so I'll try diagonal. Excellent.
Very good.
And now you can see, although I'm doing diagonal at this end, Bernie's getting kind of vertical up and down at the other end.
I'm getting a bit, yeah.
Someone else said circular? Should I try that? All right, why not? Circular? Oh, sorry. Okay.
Ow.
Okay, injury, sorry. Okay, how did you get injured? I was doing physics on stage. And you can see that the vertical part was going through. So thank you very much.
Yay.
Round of applause for our volunteers.
Oh, sorry.
Sorry.
So that's quantum superposition?
So that's Quantum superposition. It's also how polarizers work. So I'm going to warn the people in the front row now, it's going to get very bright. You might want to shade your eyes ahead of time. So these are like big sunglasses, all right? Really big sunglasses.
Show us. How do they look?
They look like Elton John.
Cool.
You know, that's a joke for your teachers. Okay, so your older teachers. So I'm now polarizing that bright light. It's too bright. So there's an arrow pointing that way. So I'm going to point an arrow this way. Did it go darker? Okay, bright? Darker. Yes? What will happen if I now put, this sheet here is quite transparent, but it's also polarizing. So what will happen when I put it in between? Will it go darker again or lighter? Lighter, darker, let's find out. When I put it this way, it's pretty dark. When I put it this way, it's pretty dark. And when I put it at 45 degrees, it's lighter.
What?
So polarizers can make invisible things visible. So there's little organisms that live in the ocean that are completely... Sorry, I'll turn it off. Thank you, Bernie.
Sorry, I still had half the light showing out one end. Sorry, everyone whose retinas were burnt out there.
Okay, for those of you who need a guide dog to get home, let us know. So there's little invisible things that live in the ocean that are transparent. They're little transparent bags of water, and you can't see them, but they're full of sugar, and it turns out sugar is polarizing. And so if you can see with polarizing vision and you live in the ocean, you can see these invisible things to eat them.
No
So there's a
way.
whole ton of animals, bees, mantis shrimp, there's a whole ton of things that can see polarized light. Has anyone heard of fireflies?
Yeah.
Has anyone seen a firefly?
Yeah.
What? In real life? Where? I saw it on YouTube. Okay. I guess YouTube is real life, but I meant flying around in your backyard. I'm not aware of them being in Brisbane. Maybe there are, but there are parts of the world where there's a lot of fireflies that come out at dusk. And they have on their bum 2 little things that light up. And it turns out at least one of them on their left buttock, it makes left circularly polarized light. And on their right buttock, it makes right circularly polarized light, and nobody knows why. Anyway, so polarization's everywhere. Okay, so how do we send information around? We can send it with color. Email? Okay, no, someone said email. Great.
Yes.
How do you get an email? Internet. Okay, so the internet. You use Wi-Fi at home? Yes. Okay, the Wi-Fi router in your house is plugged into what? A wire in the wall. And that wire in the wall goes out to the street, and then it's plugged into a glass cable. We don't use electricity to power most of the internet. Most of the distances we use glass fiber. Why are we using glass fiber? I'm going to show you that. Ben, can I borrow you and a bucket, please, and Tamara? So we're going to show you this now. Whoops, wrong one. That's just pretty.
Yeah, this one.
Okay. We're going to show you how that works using, if I can find the hole. So this is just an empty column. We're going to pour into it basically a soft drink, fingers in place.
I'm here just in case.
Tamara's here just in case. So we're just pouring in water. And if my finger wasn't on the hole, the water would be pouring out the side all over the floor, which is what happened earlier when we were practicing. So that's why my finger's here now. And what I'm going to do, though, is I'm going to show you that when I've got a difference in materials, so in this case it's between water and air, but for the cases of glass fiber, it's glass and air, you can use that to guide light. Okay, so can we kill the stage lights, please? What I'm going to do is shine the laser on my finger. It's going to burn a little bit. Okay. All right, great. So we can see it lighting up beautifully. Right now, woo! Can you see the light going down? Okay, so that, thank you, Tamara. So we are bouncing the light down the inside of the column, and we have made a very short-lived optical cable made of light that's going all over the floor. And Tamara, sorry, hang on, there we go. And you can see it's not the best way of sending light around, but it's sending it round a right angle.
Wow.
So that's how fibre cables work. And we're going to run out. Oh, it's still working. Oh, okay. We're about to pee here, so. Okay. Okay, stage lights, please. Thank you.
If you turn it back there, now it should be done. Oh, not quite, not quite.
So I'll leave my beautiful assistants doing the wet work. So what does that tell us? It tells us, A, don't do this at home. Or at least, if you do it at home, tell your parents you saw it on YouTube and not at a school trip. Secondly, it tells us this is the thing that drives the internet. Glass fibres can be thousands of kilometres long and send light information thousands of kilometres. The information they're sending is the colour of light, the polarization of light, and also how bright the light is can send information as well. Now, I want you to all do one last experiment. I said, you know when you did the Mexican wave before, we started them together and you met in the middle and the thing just died, right? That's called interference. And when two waves meet and they die, that's called destructive interference, which is a great name. Now, the way you can tell light is a wave is you can see destructive interference. I want everyone to grab their finger and thumb and hold it as close together as you can without it shaking and look at one of the bright lights
And
up
it's
on the
not
stage.
touching. It's not touching, is it?
It's not touching,
close.
just almost touching. And if it gets very close, can anyone see like a little black sausage floating between their fingers?
Yeah.
That little black sausage is you interfering the light waves from that light source, and
Wow.
it's destructive interference between your fingers, and that's how you know light is like a wave. So you can go home and show that to your parents. Thank you for your attention.
Woo! Oh,
And I'll pass back over to Bernie.
Hey, don't you go
Oh,
anywhere.
Checking you as well.
That's all we've got time for, but what do we think of physics as the language of the universe? Keep that going for our three professors, Ben, Tamara and Andrew. Woo! I reckon we might have time for one or two questions. So have you got a question ready to ask? Has anyone got a question there? Yep, call it out to me and I'll repeat it. Why? Okay, so with the light waves, something is looping, but why could something be too slow to see them? Yep.
I'm not sure I understand the question, but normally what happens is the fastest you can send information is at the speed of light, which is why it takes a long time. Those pictures of the universe from 13 billion light years ago, it took 13 billion years for the light to get to us. I know that didn't answer your question, but I'll try and find you
That's okay.
afterwards.
And is that another question over there, or is that someone scratching their ponytail? Ponytail scratch. Okay, yep, we've got a question here. Yes? How does the what? Oh, how does the disc spin? How does
How's the magnet work?
How does the... oh, it's still going.
Oh my
this.
God,
How
it's
does-
still going.
Andrew should put it
I
back
just
in.
put it out.
Oh.
I love it. I love it.
The way it's spinning is it doesn't want the magnetic field inside it to change very much. So if it was going to fall off, there'd be a big change, and spinning is just a small change, and that makes it much happier.
So it's all those electrons working
'cause
together
they're
to
work-
keep
yeah.
the magnetic field out.
Exactly. Teamwork.
All right. Oh, I think we're pretty much out of time. Is it a very easy question? Okay, what's your very easy question? Have you pushed the disc as fast as it can go?
So we used to have 2 discs. And we tried this experiment, and it shattered all over the floor.
So that's...
If you give it a big push, you'll knock it right off.
Yeah, but we won't be doing that today because budget, you know. All right, it stopped. Okay, it stopped. We're stopping. Thank you guys so much for coming along today to World Science Festival Brisbane. Woo! We'll see you next time. Have fun with your science.
Thank
Be
you.
kind to your teachers.
Thank you, Bernie.